All right, we're now going to look at the second case for how to deal with constant coefficient linear homogeneous differential equations. So where we left off last time, so we have a differential equation in this form. Again, it's A, B, and C are constants. It's linear. There's only Cx by itself, but also it's homogeneous. So there's no explicit mention of the independent variable. So we're going to make a guess. And the guess is that we expect the solution to be in the form of an exponential. So we write the most general exponential function we can. We're going to plug it in and ask what it implies. So we take the first derivative. Derivative of the exponential is the exponential times the derivative of nt, which is n. We're going to need a second derivative. And so we're going to multiply by another n. Now we plug this into our differential equation. So a times the second derivative gives us re into the nt n squared plus b times the first derivative is b times re to the nt n, and c times x. So we get c re to the nt is equal to 0. And then we ask, what does this imply? First thing we note is that we see an re to the nt in every term. So we can factor that out. So the first term becomes an squared. Second term becomes b times n. Third is c. And now we recognize that this is our solution x. We don't want r to be 0, otherwise there's 0 solution. So we require that this is 0, which means then that n is minus b plus or minus square root of b squared minus 4ac all over 2a. Right? And we get that from the quadratic formula. And as we saw last time, there's 3 cases. First case is that b squared minus 4ac is greater than 0. So the thing under the square root is positive, and that means we have 2 solutions. Call them n1 and n2. And that means that our solution then can be written as r1 times e to the n1t plus r2 e to the n2t. And we saw a number of examples on that. The second case, which we have not addressed yet, is with b squared minus 4ac equals 0. And we get one solution, which is just r1 e to the n1t. Because the thing under the square root in this n1 is going to be minus b over 2a, because the square root is 0. This is a problem because we need to have 2 solutions or 2 unknowns because we have a second derivative. And this is what we're going to focus on today. But keep in mind, what we're going to do next is what happens when b squared minus 4ac is less than 0. When that happens, we're going to have complex values for n1 and n2, and we're going to have to figure out how to deal with this. And what we're going to do is we're going to use Euler's formula and take advantage of the idea that e to the I theta is cosine theta plus I sine of theta. Okay, so let's focus now on case 2. So we're going to assume that b squared minus 4ac is equal to 0. So our n is minus b over 2a. Remember, this is coming from an equation of this form where a, b, and c are constants. And again, it's homogeneous because of this 0 here. So we need a second solution. And what we're going to do is we're going to do something that we're going to call reduction of order. So the idea is I know that r1 e to the n1t is a solution, so I want to take advantage of that and build on it. I'm going to assume a solution is of the form some unknown function g times n1t. And then I'm going to ask, what does this imply about g of t? And if I can find a g of t that's not a constant, that's going to give me my second solution. So I'm going to plug this into the ODE and see what it implies on g. I'm going to focus on g of t with the idea that this thing right here, I want it to be a solution to my differential equation. All right. Keep in mind, I'm going to have to use the product rule. So I have to remember that the derivative of u of t times v of t is the derivative of the first times the second plus the first times the derivative of the second. So I'm going to do that. I'm going to take two derivatives of this and then see what happens. So what do we have? At this point, we now have our differential equation. We know that an squared plus bn plus c equals 0, and there's only one solution that looks like minus b over 2a, and b squared minus 4ac is 0. So we're assuming this is all what's happening. And I'm going to know that e to the nt, where n is minus b over 2a, is a solution. And I'm going to assume a function of the form g of t times e to the n1t is a solution. And I'm going to ask, what can I figure out about g of t? And again, if I get something that's not a constant, it's going to give me my other solutions. So I have x of t is g of t e to the n1t. First derivative, well, I'm going to use the product rule. It's going to be g prime times n1t plus g of t. Derivative of e to the n1t is e to the n1t times the derivative of n1t, which is n1. Now to take the second derivative, notice I've got a product here and a product here, so I'm going to have to use the product rule twice. So the derivative of the first term is going to be the second derivative of g times n1t plus g prime, and then I'm going to take the derivative of n1t, e to the n1t, which we've already established is e to the n1t times n1. Now for this one, derivative of the first is going to be g prime. Leave the second function alone. Now I take g of t times the derivative of the second, and that's, oops, I got to be careful here. I forgot an n1 here. Sorry about that. And this is going to be e to the n1t. I already have an n1, but when I take the derivative of n1t, I'm going to have a second n1. Notice this term and this term are the same. So let me clean this up a little bit. I have two g primes, e to the n1t, n1, and I got g n1t, n1 squared. All right, so now I'm going to plug this into that term. That's going to give me a times g double prime e to the n1t plus 2g prime e to the n1t n1 plus g of t e to the n1t n1 squared. For the bx prime, I'm going to use that expression. So I'm going to have plus b times the quantity, g prime e to the n1t plus g of t e to the n1t n1. And then finally, I've got c times x. I'm going to use that. So I'm going to have c times x, which is g of t e to the n1t. Now, if I just focus on the terms that have g of t, I've got that term, and that term. So let me bring those together, and the other three terms, from here, here, and here, I'm just going to let them move along and see what happens. So if I multiply through by the a, I've got this term here. Multiply this by the a, I've got 2a g prime e to the n1t n1. And then for this term, I'm going to have multiply through by the b. I'm going to have b times g prime e to the n1t. Now these three terms that just have g, notice I can factor out the g. Okay. Also note each one has an e to the n1t, so we can pull that out. So here I have an a times n1 squared. From here I'm going to have b times n1, and here I'm just going to have plus c. I already know that n is a solution to this equation, and I know that e to the n1t is a solution to the homogeneous equation. So I know that this is equal to 0, which means I'm only going to be left with this for my differential equation. And keep in mind, I want this all to be equal to 0. So my new equation now becomes a g double prime e n1t plus 2a g prime e to the n1t n1 plus b g prime e to the n1t all equals 0. Okay. I also know my n1 is minus b over t2a. So I can take advantage of that and bring this in right there. So I'm going to have what? A g double prime e to the n1t plus 2a g prime e to the n1t. Now for my n1, I'm going to replace it with minus b over 2a. And the other terms stay the same. Got a 2a there and a 2a in the denominator, so those cancel. So I now have a g double prime e to the n1t plus g prime e to the n1t times minus b. So I simplified this, and this I'm not going to do anything to that term. And note, that's the same, that's the same. The only thing that's different is a b versus minus b. So these two terms cancel, and in the end I'm only left with that, where a g double prime e to the n1t is 0. Okay. Now for my original differential equation, what did I have? Because it's a second order equation, I'm assuming that a is not 0, and e to the n1t is an exponential function, so it cannot be 0. This implies that g double prime is 0. So the question now is, what is g? Well, I'm going to get rid of one of the derivatives by taking the antiderivative. Antiderivative of g double prime is just g prime. Antiderivative of 0 that is just going to be a constant. And I'm going to call that constant K1. And now I take the antiderivative of both sides again to get G. So the antiderivative of this is going to be G. Antiderivative of K1 is K1t plus K2. So my G is just a linear function. And I defined my x to be g of t times e to the n1t. So that means I have that for my solution. Let me rewrite that. So again, my original differential equation was ax double prime plus ex prime plus cx is 0. A is not 0. And I'm assuming that n is minus b over 2a. We'll call that n1. And that an squared plus bn plus c is 0. And this is the only root. And that means one solution I can write in the form of r1 e to the n1t. Another solution can be written in the form of g of t times g of t times e to the n1t, where g is k1t plus k2. And if I multiply that through, I get something in this form. And notice that term is exactly the same thing as this. I'm just calling it the constant k2 instead of r1. This looks just like it, except I'm multiplying a t. So I'm putting a t in there and changing that instead. So what does this mean? This means I have a constant coefficient linear homogeneous equation. I have one root to this, which implies that I can figure out what that root is. Then, for my solution, I know one of my solutions is that, and I can just go ahead and write the second solution is the same thing as that, but I can just multiply by the t. So if this is your only solution based on this equation, you basically can just take what you have and multiply by a t.